Semen is software architect at Nokia. Please come on. So Semen works currently in 5G U-plane. He has over 15 years of experience in embedded systems and telecom software. He's passionate about clean code robustness, design clarity, and performance. And the fun fact about Antonov that he can ride a bike and play a guitar in Italy. Ladies and gentlemen, Semen Antonov, safer APIs in C++, applicative use over risky get. Warm welcome.
Okay, I hope you'll not be having the same problems with me. Like, I'll try to be a bit more smooth in translation. Yes, hi everybody. So I'm Semen Antonov, and I want to guide you through this topic where, like, not only the tooling, but also the way you approach the coding, you can be looked a bit different. And then, like, instead of getting something, you can start using something and enjoy it. So here's the agenda. Like, first point, actually, ideally should be skipped because everybody is doing this. You can check it on the last year conference, like somebody summed it up very good, and I got the references. And yes, then we go to some examples of problems which you can find out in your code bases. Then we touch tell don't ask principle, which somehow adheres here very good, and try to define a perfect error, what it could be like, which properties it could have. And finally come to applicative pattern and try to explain it in a human readable and human understandable way. So, yeah, as said, this first part is highly inspired by different references I attached in the end. Like, hopefully you get the slide set. There is really a lot to read on the topics of error handling overall and in C++ in particular. And I just run through here for like fast that we are on the same page, highlighting what I want to highlight, and like the particular implementation you can reach out like on these other talks or on the internet. Like, here's a list, and maybe I don't have the timer running, so if you can start the timer there would be very good. Or okay, anyway. Okay, I also can use my watches. Sorry. Yes, so the first one, this error no, is that, not be talking about this, and I skip also intentionally asserts and contracts because it goes a little aside of what I want to show you, right? And applicative part we talk in the end, so it's not in the first chapter. Yeah, let's define our playground class. Like, some people know this kind of event classes in our project, and for those who don't, so imagine you have a class which allocates and owns memory for you, right? And you like want to buzzer it to get some pointer or reference where you want to write your data to fill in the event, right? And then when you send this event, so the memory is gone, and you probably cannot the place where you can write something. And what we want to approach is how we can safely fill the memory inside of this class, and do it also nicely from interface perspective, so people don't make mistakes. And people do make mistakes, actually, if you see the history. Yes, and how we basically will do the error handling for this get message. And let's start, like, maybe not 9 AM start, but with row pointers. Like, if you want to return something since forever, you can return null pointer, right? Okay, if you have the memory for this allocated, definitely. But in this case, we do have. And like, if something's there, you return normal pointer, not there, null pointer, all good. Problems appearing here, people by some reason tend to forget to check for null pointer, especially if they're pretty sure that problems would not happen. And they usually do not happen, right? But usually doesn't mean always, unfortunately. You cannot, in this case, distinguish with like which error is happening there. And historically, some people can still, by some reasons, they can still mix it up with manual memory management, which we hopefully don't do at all in C++ nowadays, right? So next one, also apparently common in the minds from what I have seen in different places. Like you can return a dummy value, and on its own, returning a dummy value as a way to handle an error is doable approach. Like especially if you have like some bulletproof, always available, always correct, which doesn't make problem a value for you to return, all good. If you want to return something more complex, like here, something you have to fill, I don't know, maybe some vector or some more complex structure where you can set some sizes and then you have some expectations on this, what you fill there. Then you end up having things like undefined behavior and crashes in the end. And this is what you probably don't want to have, right? So the next one is reversed, basically. So you return the error code or like, okay, something went wrong, like it can be a Boolean, and you make it no discard. And that's a great tool. Like no discard, you cannot then forget to check about this, right? Like to check the value returned. You can still forget to stop the code execution afterwards. And I also have seen cases like this. And like here, you provide this in-out message where you write then whatever you like. You write the pointer, the correct one, if you have everything, and then you can later on fill it, right? And feel good. Overall, this in-out parameters actually are not recommended by CPP core guidelines, and there are reasons. But yeah, and to highlight no discard is really a great thing. We come back to it later. The next one, this one is recommended by CPP core guidelines. Like you can throw an exception, right? What you get from this? You get a perfect success case code. You get great central error handling, right? It can be, according to some measurements, actually almost the fastest way on success path to have error conditions, right? Yes, but it comes with some problems. And despite like there are quite many cons here, it's still a great tool. So I just tried to highlight what can get problematic and why some people don't like it. And for us, like in our project, like this hard real-time part is not too good. And it's said in many places, like if you are in hard real-time systems, you have to consider if it works for you. Then like, yeah, the first point, it's really have to be used for exceptional cases, and there are different reasons for this, like starting from performance, because fail case performance can be very bad to okay-ish. And like there are, I attached the talks where somebody is trying to really optimize it, and maybe they get it to some common ground, like to have really much faster exceptions in C++, hopefully, let's see. But like other reasons, for example, if you want to distinguish between exceptional situation and not exceptional, like which like user can have some failures, like they can provide you wrong input or whatever, or like do something according to business logic, which can happen, but it's not a showstopper. And also logically, you sometimes want to differentiate this, right? But what we get, in the end, we get unpredictable interfaces of errors, so you're not pretty sure what and when can throw, right? Then you have to really take carefully things like RAI, so you shouldn't have any manual resource management, and maybe memory management would be of a list of a problem, because we have like lots of tools to find it. For your manual, whatever, arrays, you have indexes and you have some tokens, like this you can really lose easily in case of exceptions, unless you use RAI, right? And you can also get into troubles in case of corner cases, like some function decides to throw while you are in the destructor, for example, or while you are in the process of handling the exception. And it can get problematic. And there are many talks explaining pros and cons of exceptions for sure. Next one, a relatively new tool, right, in our C++ world, like optional and expected. You get clear, predictable interface. With expected, you get also possibility to nicely propagate the error object code, how you like it. You get more decentralized handling code, error handling code, right? But unfortunately, on its own, if you use it not wisely, it can be actually not much better than a raw pointer, because like if you access it with operator star or arrow, without checking, you surprisingly get to undefined behavior, like even not a crash, at least till C++ 23 and 26 sometimes, right? And I even tried, like when preparing some code for the talk, I bumped into this kind of problems. And they have, but what's good, they have really support and like, yeah, you can use it in these monadic approaches or with applicative use. So, and this we'll see later on. Let's go to common errors. And yeah, start from the dummiest one. So somebody creates an event and say, hey, I just want to fill something, and it works for years, 5, 6 years, unless you start bringing your system really on the edge, and then you start lacking some memory, and then sometimes it doesn't work. Bam. So you crash usually if you return pointers, for example. Then like you can forget to return. Like you have to check before usage, you know this, but then you are really tired and you just forget to write this return. Unfortunate situation, bam, you are ending up in the problems. Then here you stop the code execution, so you will not crash, but it was not clear for the user of your interface who should handle this error. And apparently event class decided that, like imaginary event class decided that it's not its duty to produce anything in case of problems, and you decided that it's not your duty to print anything or produce any kind of error code in case of problems, and then you get hidden errors, which sometimes quite comparable to like crashes, because debugging can get to nightmare, right? And unless you have a clear strategy, you will continue ending in these kind of problems. And here, like, I added a bit more code on the slides with every next slide, just to show, like, when you increase the complexity, it really gets tough at some point. Here, like, for example, you see this bulb. So this is usually something cool, and the bomb is usually something suboptimal. So somebody make a function, send everything, right? And for sure allocates, and okay, I checked everything, right? I have the memory, I can go further, I have a loop, and I push in my event from some container or something, and yeah, and all works good. And then somebody comes to an idea, okay, when it's full, I can actually send the part and reallocate the memory and continue working, right? But then apparently reallocation fails, and you do not handle it properly enough. Then you exit to the loop again, and you bump, so you crash in line 230. Even so, initially you actually have checked for the proper memory availability. Let's get it even more complex. And so now we had it complex in space, right? We get more code, and we can add one more dimension here, time. So here, easy function. So you prepare event, you fill some data there. You are a very good programmer. You, on the entrance to this function, you check, all good, memory is there, then I can do everything. I have my private methods, which access my event, like as a member of the class, and write something there, and everything is fine. One public method, one check. You don't need to check it additionally, right? Because performance matters. Unfortunately, comes the future, and somebody writes something like this. This somebody newbie, like 2 years ago, sends you a small patch, said, hey, I want to reset data, like, can you approve? Looks good. And you're like, okay, looks good. There are even some unit tests for this. All works. Unless it doesn't, because in case the event was sent, you have not checked for memory presence, like you have to reallocate it. Oh. Like here, right, line 258. And these time-based problems are one of the most hardest one, right? Let's try to sum it up. And the first one, like why it happens. And the first is a default answers which you can give when you are quality manager and somebody asks you for quick feedback. Like it's not enough test-driven development, tools, and code reviews. Because theoretically, these three can find everything, right? Practically, unfortunately, bugs still go through it. Even so, actually, there was a review of studies that code review can find like up to 50% bugs, and it's even more efficient than unit testing in some sense, right? When done like perfectly, but we know, unfortunately, it's not always perfect. Then the second one is very good, and I really recommend to watch this talk about this common C++ errors. It's traditions. So some people still continue writing in C with classes instead of taking the modern C++ and the safety it actually gives to us. And then like tired people, too tight deadlines, not clear strategy like where, what, how you handle, how you propagate errors in your project, in your component, like what is the strategy overall behind which errors are expected, which are not. Like if you don't have it clear, you run into troubles. And the last one here is when you neglect taking responsibility for handle errors inside of your code, even if you can do it. And like, we come back to it, but handling doesn't mean hiding. So these are two different things. Then assumptions. Like, people assume, and I have seen quite sometimes that, okay, I have written cool code, I'm a professional, my colleague also a professional, like nobody else touches this code, all works. And then comes a newbie in the different side of the world and start extending this unlucky situation. Assumptions that you will never get unexpected values, and like good example enum classes where you can easily static cast to it, right? It is no problem. And if you have some value or dummy value static cast, bam, so you're out of range. The third one is very good. It's implicit knowledge about your class or about some class that you have to check for something before you use it, right? And like with standard expected, you have to check, or optional, you have to check that value is there before you access it, right? And it can be known for classes from standard library, but is it really known for classes you write? Like, do you really have this great documentation, everybody aware and nobody will make mistakes? Not absolutely, at least from what I see in my experience. Yes, and like in this point, like interfaces really get unclear if you have a lot of the need of this implicit knowledge in your system. And the last from origins, and one of the also deal breakers, is overpropagation of maybes. And by maybes, I mean many things. Like whenever I talk maybes later, I mean row pointers, optionals, expected, and even IDs to go to a database to get your context, user context, for example. Because like, or even like your event class, which can get invalid state, and it's not handling it internally, it's also like maybe. So you have to check something in advance before using it. And if you overpropagate it, it slowly or immediately, depends on the speed of your coding, leads to defensive programming if you want to be really on the safe side, because you start getting not sure, like, like, is a value here or not? And like with lots of code you have like in this class, and lots of people touching it, you cannot be sure. And to be absolutely safe, you end up doing defensive programming, right? When you do defensive programming, you immediately make performance problems. And then somebody comes to you and says, hey, what you value more, stability or performance? And you say both. but then it makes problems. Then you also get copy-pasted or very unreasonable error handling if you have to handle it in 1,000 calls across your code base. One definitely would be not correct, like the error handling which you require from users of your interface. And yes, then you end up in forgotten errors and crashes and everything. And here we come to tell, don't ask. It's kind of known but not too appreciated principle, I believe. In short, like an object-oriented design, logic and data, right, they are really tightly coupled. And if you design a class where you always get something and then use these values which you have got, you gradually move out the logic of this class outside of the class, right? And you basically couple it with some other class. And you break encapsulation by this, yeah, make some other unfortunate side effects. You can read out what exactly, like with these references 11, 12, and 13. And yes, and I like the phrase that we should really attempt to write a shy code which doesn't expose more than needed to the neighbors, right? And doesn't talk to more neighbors than it actually has to. And yeah, that's the main idea behind this tell, don't ask. And the last bulb is very good. So some people who really take it too personal or serious, they start becoming extreme get eradicators. And like, it's not always correct. So there are cases where you have a class which responsibility is just to store some list of elements, and you have to provide the accessor for it, and it's okay to have gets there, right? But there are cases where you really like export the logic outside, and that's not good. So, but why we're here? Because of error handling. And when you have anything going wrong in your code, the easiest, but maybe not the best way you can do it, you just return an error and say, okay, somebody will handle it for me. And yeah, no responsibilities, and you get no code extra to write, no extra unit tests. You are just good. You just return a value, all good. Unless you start like calling this method in many, many places in the code, and then you end up actually spreading this duty to many, many other places in the business logic. And then are you sure that if you have not found a great way what you can do with the problem, when you write in this particular code, I don't know, framework implementation, that people who will be calling this, they have better idea what to do with this, especially if they're super concentrated in their feature, business logic details. Not always, like practice says, really not always. And here let's consider error handling to be a part of responsibilities of a class. And like not just default answer, okay, just return maybe or row pointer and maybe null pointer sometimes. But some errors you can really handle internally. And it could be even the best what you can do, right? I don't know, for some technical errors, you can retry some accesses and do things like this, or we see later what we can do more. Yes, like the third point also says you can design your classes to have no invalid state. They maybe technically absolutely don't have invalid state, meaning you can fail on construction, like on the factory, just return you expected, and if the value is there, like it's there, and then you do not have it at all in the unexpected state. Or they handle all the errors which can happen internally, and then from outside world, it looks like class without invalid value, so you don't have to check for validity. And if you have these classes in your system, like you really a lot decrease complexity, because you do not have this extra overly like lots of code to check if it's valid, if it goes correct, if it's go wrong. Like you don't have to care about this because it is there, like it's actually valid. And yeah, the last good point that lambdas can help to facilitate these approaches, because like if you, as an example of event class, you want to return something like some reference, right? And you don't have memory, like what you do. You cannot return, okay, you can return null pointer, and then you end up in the same, like similar situation, somebody have to check for this. And here you can just provide the usage of what you have internally, like what you store internally, or maybe you can even provide the lambda for the error handling. And by this cancel the internal error handling which is implemented in the class. So let's come to more and more fun stuff. So the perfect error. And this part, like I like the most, like the perfect error in your system is the one which cannot technically happen, right? If you do not have possibility to fail, that's the best what you can do about the error handling, right? And here what we can do, we can try to design interfaces which do not return maybes, any kind of maybes, especially if they're really often used. And we just practically proven if you have an interface which returns maybe, especially if it fails sometimes, people get it wrong. So they just forget checking for validity, or even if they check, they sometimes just skip if problems are there, or yeah, do all kind of nonsense. Especially like if this is often used. And then like reworking this afterwards is also like really hurts. Then the second one, we should try to propagate down the call stack valid objects. Being it like this last point, this class months, which have always correct number inside storing the month's number, right? Instead of an integer, which can apparently go wrong. Like you can write there something invalid in this class months, you cannot, only upon construction. Or you unwrap it, or maybe even like don't leave the maybe context, right? And just propagate down the call stack already the values which are present, but not the maybes. And this way you can really achieve reducing the amount of the code which works with maybes, and to have more code which works with real objects which are there, right? And yeah, this one is also, I laugh a lot. So when you look at this, all these checks, if value is there, right? If it's correct, if it's in it, then with increased complexity, it really starts feeling a bit like manual memory management, right? Or manual resource management. Because you cannot guarantee that it was not invalidated at some point, especially if you have exceptions activated, right? And it can throw in some unexpected places, and you don't know, like, okay, is it actually there or not? And in these terms, like allowing unchecked unwrapping, like the star value, can really like make you lots of problems. And as you have seen in the examples, like more you put apart checking for validity and actual usage with unwrapping. So if you check for validity and then get the, I don't know, reference to this message, then it's very much more difficult to fail this, even so there are ways. But if you really like maybe checked here and then you unwrap here, a lot of things can happen in between. And really like it's great if you can collocate checking and unwrapping. You can use things like value or, for example, right? If that's a way for like to handle your errors, and sometimes it is. I mean, sometimes there are great default values, and if something goes wrong, just use them. I mean, maybe it's not doesn't make sense to inform the outer systems about this problem, but yeah, it depends for sure. Yes, about loops, I will not be talking much in this presentation. And the last but not least here, if this manual checks or like absence of manual unwraps, they hurt you, so you can consider if you actually have design problems, if you overpropagate maybes. Because if every method in your system you call returns you maybe, and then you have to check it maybe before use or propagate this maybe context up the stack, it's either your error handling strategy, and it's fine, or it can be considered design problem and overpropagation of maybes. Yes, let's talk about interfaces as we started. So interfaces should be clear about which errors, if they produce errors, and which. Here exceptions maybe have a bit of problems. Then it's great if they can communicate directly on the interface level whether you have to handle this error or it's just for your information. Like maybe I failed to send an event, but I did everything, like no worries, but here there is a Boolean flag for you, like if you want, you can do something. Maybe it can affect your business logic, right? And here you can consider like no discard as a good marker to, okay, if you return no discard expected, then it's your problem to handle this kind of error, right? You can introduce another type like unchecked error, for example, and then return it, and then everybody knows by reading the interface, okay, like this error is unchecked, I have to do something about it. And this class can, for example, has this method, I just invented it like and then or, where you provide the usage and error handling at the same time, and there is no way you just take the usage like without providing the error handling. And this way you make people like ignore error handling really explicitly if they have to. And yeah, common interfaces and often used should have really good readability and should not be cluttered with error handling code. And exceptions, I'm not saying that they're bad. I mean, they are for exceptional cases is a great tool, but really for exceptional cases and a great scope, because some people have, many people have different understanding of what is expected in the system and what is not. Yes, error handling, perfect error handling should not be repeated, and not only from code perspective, like copy-pasted, but from duties perspective. So you do not get away this duty that somebody will handle this for you, as much as you can at least. And you escape maybe context really only in the places. Like escaping maybe context would mean you get the value and then you handle the error, or you have to propagate this error up the stack, right? If that's not the place for you to handle this error. So that's the meaning of escaping this maybe context. And yeah, we should really try to reduce the number of unwraps and handle errors locally, as was said. And maybe like this one is, this 1.4 is a good one. If you're like the best error handling you can imagine for this kind of situation is just printing a log like, do you really have to propagate it up the stack? Check it out. So maybe not always. Yes, let's not propagate down the call stack maybes. As explained, let's like try really have the well-defined objects going down the call stack. Like we should not make functions to be dependent on outer problems, right? If you can propagate the real value, just it will be much greater and much simpler code afterwards. And yeah, the last one is very good. So you can anticipate impacting errors on different layers of your system. Meaning, like in terms of dummy event class, if you have the, like you didn't have managed to allocate the memory and then you do not send this event, it can be crucial for some systems, but if your protocols actually are ready for this, because you know sometimes event can get lost on the Ethernet or whatever, whenever in the network, and then you would have some retries, or maybe it's not that important events if you don't have retries. Yeah, then it's also fine to keep it as an error handling strategy and to not over-propagate the code with this kind of problems up the stack. Yes, this one is good. I'll not talk much because it's actually apparently a very big topic. So in case of error handling, we should keep consistency of the data, meaning like in the upper example, if your second line fails, you don't know what is written as this, what is not, right? And okay, here it's pretty simple set of data written, but if it gets complex, like reverting it back could be quite problematic. And here, since like RAI or batch processing can really help, and like for example, if you provide a lambda, then probably a connection to your database cannot fail, right? If it's executed as one batch of code. Yes, and the last, it's also far not complete because it's again a big topic. So debugging should be easy. What does it mean? We should be able to handle errors like with the first set of log, ideally. It should not cause you avalanche of errors. Like if one error happens, sometimes you get so many warnings and everything that it's really difficult and confusing, especially for newcomers in your system, to find out what exactly has happened. And yeah, one example, I don't know, your one component crashes and then somebody starts killing other components, and then you don't really know which of them started first, or maybe you don't have complete logs, and then you are not sure why somebody died in this particular place where it cannot happen. Yeah, you should have split of technical and domain errors, and there is a nice read why you want to distinguish expected and unexpected errors. Also, you should prefer logging unexpected errors, because expected maybe, yeah, it's just normal system behavior. And like in the sunny day tests, that's also not always happen by some reason. You should not have error logs, because otherwise, when really problems are happening, debugging gets really nasty, because you don't know, especially if you're a newbie in this area, like, is it a good error or bad error? And yeah. And the first one, yeah, if you really detect undefined behavior in your system, you want to consider exit fast, meaning crash is okay for some errors, right? Because then you can debug it at least. And the outer layers, they should be ideally ready that you do something like this, right? And then can, for example, restart you fast enough that you don't have a big interruption. Okay, why we have here applicative? Because it can be very nicely collocated with error handling. And you can read this first part, and actually many talks about applicative pattern which you open, they explain something from the first small font. But in short, like an easy words, like imagine you have a couple of maybes, like here in the square, like M1 and M2, and you want to multiply them, right? What can be easier? But you don't know if the values are there, and you do not want to know this, actually. And then you create this kind of apply function, right? You provide a lambda there, like which takes already two values, not maybes, but real values, and returns you the result of multiplication. And then writes it to the M3, and if both values M1 and M2 are available, you get the real value in M3. Otherwise, you get the something. So some unexpected error. Probably one of this M1 or M2. And that's a good way to like reduce error propagation code, as shown in this line in the reference 14. Like, let's see how we can do it. Like manual unwrapping, the most classical, I would say. So here we design a function send user info, and we operate with three maybes. One is a tracer, another one is this user ID which you get from database. Maybe it's not there. And the third one is event, known event class, which maybe cannot allocate memory for you, right? And in order to do it absolutely perfect, you end up writing this kind of code. It gets quite difficult to understand what's going on in this function, isn't it? And then you say, okay, but we know what lambdas is, right? We can design this nice use approaches, like when you say, hey, tracer, I want to write, and then you enter the scopes, and userdb you want to read, and then you like end up in doing something like Python. And here it still gets quite difficult to understand what's going on, right? Can we do it better? Probably we can. With C++ 23 to 26, depends if you want to use optional or not, you can use this range for loop and standards use zip, right? Where you can provide all maybes you like, and then they're unpacked in the for loop if all of them are present. And this could be a custom type providing begin and end, or standard optional with C++ 26, if I remember correctly. Yeah, like here maybe the point, you lose the error then. So if one of them has an error, you don't get it, and then you return in the end something like not specified, maybe. It's not absolutely friendly to R values, as I have found. And whenever you see now a for loop in your code, it's not always a loop. It can be a way to unpack an optional, right, or a set of optionals altogether. But can we do it better? Some libraries, or actually many libraries, like Boost, for example, they have this try maybe context concept where you provide your maybe to the macro, and to the macro, because language doesn't support it, you provide the name of your variable, and then if value is available, you get this, like in the 408 message variable assigned the message from event, right? Otherwise, you return. So basically, you cannot continue. And it's pretty nice code, actually. It looks not too bad. And you can extend it with requiring like try maybe or, where you provide the lambda, and then lambda decides what you return. And then you can maybe return some default values if you want, or print extra logs, but you still cannot continue going further if you use this kind of try maybe. But can we do it better? I created this class as a proof of concept. Like, let me highlight it with, okay, running out of time. It can apply a function to multiple maybes, basically what applicative pattern is for. It supports actually wide range of maybes, like everything I have listed, and in this implementation, basically everything which have a pointer-like interface, like can be casted to bool and has operated star. It unwraps the standard reference wrapper for instead of you, just to make your life nicer. It traces your, like, where errors appearing from with standard source location. So when you create this error and propagate it to standard expected, you get where it comes from. It's very nice. And then, okay, I skip something. So it can be used to implement your applicative interfaces, your interfaces of your classes which behave in applicative manner, and yeah, making it very user-friendly in the end. So how you use it? I do not concentrate on implementation of this proof of concept. You can go and see, and it's in Compiler Explorer, how it optimizes. And it actually does optimize good, but please be sure to remove this address sanitizer as compile flag, because, yeah. And so you get here the business logic in the middle, and in the end you get this maybes, and in the beginning this usage of this maybe class. So it gets much more readable already, but can we do it better? Yes. So for example, I implemented here also the way to zip it for all maybes, deducting the error codes if they are like for different types. And then like in line 400, you can return a real error which has happened in one of these maybes. Like, otherwise, it looks like a normal this zip view, and should behave with similar performance actually. Can we do it even better? And as I said, like you can use it to integrate it to your custom classes, right? And to custom interfaces. And here, like imagine you have the send method, which takes a filler and a set of maybes, and then you enter in the scope. And when you enter in the scope of your class, you can do a lot of cool things, like you can measure performance of filling of your events. You can do the scope prefixing of logs, right? Where you, like everything which then executed inside of a Lambda would have some prefix that, okay, it happens because of this event, for example. You can do like some statistics, and so everything which scopes brings you. And then like in line 465, you use this maybe and then unpack everything and prepend the message in the beginning. And if it goes wrong, or it goes right in 466, you actually send the event. And here how the usage would look like, right? And what I like here is that we really bind the most important action of this function, right? And we make it really screaming, okay, here this function is about sending something from the event class, not about unpacking the maybes. And the maybes which you unpack, they come in the end. Yeah, so let's compare it with the first approach, where we do it with the classical ifs. So that's a part of the code we lose, right? But we still keep it implicitly. But can we do it even better? And I have like maybe 1 minute, so not too much better. Yes, we can ask the question, okay, but why we actually propagated maybe to this send user info? And is it responsibility of this function to cope with problems with tracer or with absence of user? Like maybe we can do it up the stack. Maybe even we can reuse results of these upstack calls, right? And here, like on the left, you see we actually extracted separately with this maybe and then, and we use this tracer for some timer tracing or something else, and we use the user for extra statistics, and actually otherwise we would have to do this unpacking every time. We would have to extract this user from the database like every time, right? If you have a code like this. And maybe this send user info really doesn't have to care about these problems, right? But you still get this nice send interface, so which accepts maybe for future. And you get like well-defined values inside, and then you lose your maybe context in line 544, right? If something goes wrong, then you bubble up with all your errors there, and then you send the failure as a response. So this looks pretty nice. And let's jump to takeaways, and maybe to questions if you would have a bit of time. Yes, expect that newbies will touch your code, so and it should be made safe enough for them as well, like not only for you as a creator. Then the perfect error, it's the one which cannot happen. Like if the error technically is not possible, that's the best what you can do, right? And here, like you can handle it internally, use this tell on task. Lambdas would help you. You do not overpropagate maybe values, especially down the call stack, and up the call stack on commonly called methods. Yeah, the third one. So manual object state management, like if it's valid, it feels very similar to manual memory management. So it mostly works, but unless it doesn't. And this doesn't, then you end up debugging on long weekends, right? And here you can avoid unchecked unwrappings and limit escaping from maybe context, really to the places where you have to handle this error and like where it's the best place to do it, right? And the last but not least, applicative approaches can save you a lot of writing on error handling and on error propagation code, as I have shown. Do you lose me? No? Do you hear me? But we are here, so we are in the end. Thank you.
Big round of applause again to Semen. And now we'll take, we are just on time, so we'll take just maybe 2 questions. So questions from the audience. I don't see questions. Oh, here is the question, so please go ahead.
Well, no. I do hear, but others maybe not.
Yeah, I guess now. Yeah, so thanks for the great talk. I wanted to just ask one question about this maybe class that you've written. Is it prepared to be extended by other user-implemented maybes? Because the ones that you foresaw in the implementation, maybe this is just not the full set. Maybe the users of your class will have their own kinds of maybes in their code base. Is it possible to inject them into your class?
Yes.
Awesome.
Do you hear me?
Yes.
Okay. Yes. So basically, everything which has interface of a row pointer. So I taken this operator star and cast it to bool. All works then. So you can feed it and it would behave in applicative manner. I even designed my way to deduct errors, like, because if you have an expected, you have the error inside, you can take it and propagate it, but if you have a row pointer, you don't have an error inside, right? But then I invented something like you put some null pointer error code and then you return it. So you can still return this up the stack, the error codes. And you can like use type traits, for example, to have this error code deduction for your classes if you want.
Yeah, that sounds good enough. Thank you.
And yeah, it's a proof of concept, it's important, and I tested it somehow. I mean, it's based on the real code, which you do not copy-paste for the conference, and here, like, I did my best not to make bugs. It should work. If you put it in production, write a couple more tests. So.
All right, thank you. We are running out of time, unfortunately, so no more questions. So big round of applause again to Semen. Thank you very much.